Similar to the previous projects done in UAV class, the engineering design process was once again a significant component to the completion of the Amazing Supersonic Decelerator project. First and foremost, I needed to be well informed on the purpose and objective of this new project, which was to design and test a drag device to slow an aircraft and protect its cargo, as well as calculate the surface area and measure the mass of the aircraft using the engineering design process. However, in order to begin working on this project, I needed to review the engineering design process once again. The engineering design process consists of 5 components. The first one is to ask, in which you identify the problem that needs a solution and pose questions to clarify conditions and constraints. Next is imagine, in which you brainstorm possible ideas that might be developed as a solution to the problem. Next is to plan, in which from the list of proposed ideas you select one solution that seems to address the problem while meeting the required design constraints. Next is to create, in which you build the model or prototype selected. Next is to experiment, in which you evaluate the design by testing the designed product to see if it works and meets the requirements of the desired solution. And lastly, it is improve, in which you make necessary modifications and continue to retest the design until the final design successfully addresses the problem while staying within the required design constraints. Once I reviewed the EDP, I began the first step and started asking significant questions relevant to the project, such as: what are my constraints in respect to shape? What are my dimensional limitations? How will I determine the surface area of my decelerator? What outside factors will impact my decelerator? What materials can I use? And lastly, how will I ensure that the aircraft lands vertically? The next step in the EDP is to imagine, for which I discovered potential designs for my inspiration while taking in consideration the restriction that the decelerator could not be circular. A few designs that caught my eye are a hexagonal parachute, a triangular parachute, a triple-double parachute, and a square parachute. The next step is to plan, and so I chose the design below as inspiration for my Amazing Supersonic Decelerator, as it addressed the problem while meeting the required design constraints, such as shape. The Amazing Supersonic Decelerator assignment had a packet attached to the objective and directions, which consisted of a step-by-step approach to the project. The first section of the packet was plan, and its first assignment in it was to draw and label my drag device and be sure to include measurements. And the next assignment was to write a hypothesis that describes how the surface area of the drag device will affect the time it takes for the payload to drop. The sketch I drew is shown below, and as you can see, instead of a simple hexagonal parachute, my group and I decided to make a hexagonal prism parachute. We believed that this design would be more efficient, as our initial thoughts were that the hexagonal prism will be able to capture an abundance of air and force the cargo capsule to fall slower, and that the extended string connecting the hexagonal prism and the cargo capsule will give the parachute enough room to expand and capture the air while it's falling. In response to the second assignment, I created a hypothesis, which was that if the surface area is increased, then the drop time will also increase, and vice versa. In other words, the surface area is directly proportional to the drop time of the drag device. After making hand-drawn blueprints for all sides of the parachute, I once again used the software SketchUp and created a 3D model for it. The next step in the engineering design process is to create, And so I began to collect all the materials that I will be using to make my drag device. The second section of the packet was experiment and record, and his first assignment was to record the drop height, and the next assignment was to drop the drag device attached to the capsule while timing descent. To determine the drop height, my group and I measured the distance between the floor and the balcony. Next, I was in the experimental stage of the EDP, and so I did the second assignment in the experiment and record section. First, I measured the surface area of the parachute by calculating the area of each side and adding it, as shown in the image below, and then I recorded the following data. The final step of the EDP is to improve, and to do so, my group and I decided to create a second parachute to add to our first parachute in hopes of elongating the drop time. Once the parachute was created, I took the surface area using the same method as before. And this is the final data collected, which shows that adding a second parachute did indeed extend the drop time. The next and final section of the packet was conclusion, and the assignment within it was to answer reflection questions. The first question was that which drag device characteristics provided the most reliable results and why. I came to the conclusion that having a double parachute had the most desired and reliable results because it provided more surface area to the structure, which made the drag device fall slower, not to mention that having multiple parachutes provided more stability. The next question was that what was discovered about the relationship between surface area and drop time or speed. I discovered that my hypothesis was correct and that the surface area and the drop time are directly proportional based on the data that I collected. The next project was to assemble a 450mm drone with a group and eventually fly it.
Where is my binding device? Insert it. You cannot bind it without it.
Wow, bro.
After successfully assembling and binding the drone, I had to install the camera, which meant switching the camera to a frequency and channel adjacent to the frequency and channel of the display screen. The importance of this was to learn about different frequencies and channels and how they affect the relationship between the camera and the display screen.